Hello everyone. Now in this class we are going to learn about residue and residue theorem. Now first look at the definition of residue. Now the quotient of 1 by z minus a in the Lorentz series expansion of f of z is called residue of f of z at the point of z equal to a. Now first look at the quotient of 1 by z minus a in the Lorentz series. I will consider the general Lorentz series expansion here. F of z equals sigma n equal to 0 to infinity a n z minus a whole power n plus sigma n equal to 1 to infinity b n by z minus a whole power n. To get the quotient of 1 by z minus a, now here they are positive, they are negative terms, right? Here negative term 1 minus z minus a. Now 1 by z minus a whole power 1, nothing but the specific value of n is 1. Now put it for n equal to 1. Now b1 is a quotient, right? Now simply residue of f of z at z equal to a is b1. Now that b1 we can look at it, b1. Now n equal to substitute 1, get for b1. The substitute here b1 is 1 by 2 pi integral over c f of z by z minus a whole power n equal to 1. Minus 1 plus 1 is 0, right? So this term is 1, right? Something power 0 is 1, nothing but only f of z dz. That is a b1 that we represent with the residue of f of a. Nothing but f of z at z equal to a, residue of f of a. Using this formula you can find the integration also. Now that integral over c f of z dz equal to, now 2 pi right at this time, now 2 pi into residue of f of a. Okay. Now this is the definition of residue. Now next look at the residue theorem. Okay. Now first look at the statement. If f of z is analytic in a closed curve C except a finite number of singular points within a C, right, then integral over C f of z equal to 2 pi times sum of the residue at that singular points. Okay. Now this we need to prove it. Okay. To prove that, first I consider a C including that C having for finite number of singular points. Okay. Singular point definition is what? The f of z at that points are not analytic. Okay. Now I take a finite number of points here that I let for a1, a2, a3, a4 and so on an. At these points f of z is not analytic, nothing but they are singular points. Okay. Now next now we need to consider a small circles over that singular points. For a1 singular point is c1, for a2 singular point is c2 and so on, for an singular point is cn. Okay. Now look at the theory, but what we discussed that we wrote here. Let C is a closed curve having n singular points, finite number, that is say for a1, a2, a3 and so on an. Consider small circles with c1, c2, c3 respect to the singular points. By connecting all these points, now when you connect it here like this, let's say here a, b, here a dash and b dash. We have other singular point is here a3. When you connect it like here c, d, c dash, d dash. Okay, like that we need to connect it here. Now to connecting that, the over c integration f of z dz using by using Cauchy theorem, integral over c f of z dz equal to integral over c1 f of z dz plus integral over ab, first line. Here we have two lines, first line ab, next integral over c2 f of z dz plus cd, next integral over c3 f of z dz and so on for integral over cn f of z dz. Now again you can reach this like in reverse order, like c dash, d dash, again b dash, c dash, dz. Now these AB and A dash, B dash, we have the same length, right? Near to same length. Now here C dash, D dash, CD having same length, but in a different direction. First go like this, one direction, again come like this, we have the different direction. Therefore they are cancelled, right? Same quantities, having different direction, simply they are cancelled. Okay. Now remaining we have integral over C1 f of z dz plus integral over C2 f of z dz plus and so on integral over Cn f of z dz. Okay. Now for this integral over C1 f of z, integral over C1, now A1 is a singular point. Now at that singular point we need to expand as a Lorentz series expansion having the power z minus a. For that Lorentz series expansion, to get for integral over C1 f of z dz. Now what is the integral over C1 f of z dz? By using the residue, simply, now I'll see here the formula just we discussed. Integral over C f of z dz is 2 pi into residue at a singular point, right? Now here in this C1 circle, C1 curve, A1 is a singular point. Now we need to expand the Lorentz series expansion of f of z having the powers of z minus a1. In that 1 by z minus a1 quotient is a residue, that is a b1, right? Now the integral over c f of z dz is 2 pi into residue at f of a1, right? Now 2 pi into residue of f of a1. Okay, now this is for first term, plus integral over c f of z dz, integral over c f of z dz. In C2, A2 is a singular point. We can expand as a Lorentz series expansion of having the power z minus a2. Now in that integral over C2 f of z dz is 2 pi into residue of f of a2. Okay. Similarly, we have other terms also, plus and so on for Cn, 2 pi into residue of f of an. Okay. Now 2 pi common it. Now residue of f of a1 plus residue of f of a2 plus and so on residue of f of an. Now that can be our summation of residues at singular points, right? Now 2 pi into sum of the residue at singular points within a C. Now this is a way to get the proof of the theorem. Now next look at the some of the points to find the residues. Okay. Now most often you can use these three formulas to find out the residues. Now if f of z has a simple pole at z equal to a, then we have the residue formula, residue of f of a equal to limits z tends to a, z minus a into f of z. Okay, one formula. Now other one, if f of z can be written as pi of z by psi of z, then residue of f of a equal to limits z tends to a, f of z by psi dash of z, psi dash of z. Okay, now next we have a pole of order n. The pole we have order n. The general formula, if f of z has a pole of order n at z equal to a, then residue of f of a equal to 1 by 2 n minus 1 factorial into dn minus 1 by dz power n minus 1 into z minus a whole power n f of z at z equal to a. Now these are the formulas we are going to use to find out the integration of f of z. Okay, thank you.